Hello. So, in this example, we are going to be finding all the local and absolute maximums and minimums. So, this is one of those things that is sort of the most common aspect of a lot of applications. So, a lot of applications in calculus boil down to sort of modeling a thing and then finding sort of the best possible aspect. So, this is like optimization and things like that. And usually these like best outcomes, whatever they are, they tend to occur at maximums and minimums because that's sort of what they're supposed to represent. So for that reason, we're going to have sort of a bunch of these videos. So in this one, we have this sort of nice polynomial. We want to find all the maximums and minimums. So remember, the idea here is that maximums and minimums occur sort of where the derivative is zero. That's sort of the way it's normally sort of presented. But maybe a better or more sort of accurate way of thinking about it is it really occurs when the sign of the derivative changes, right? So it's true that they do occur sort of at zeros of the derivative, but not all zeros of derivatives are max or mins, right? They're the critical points. They might be, and that's because if the sign doesn't change, then that's not a max or min, okay? So with that being said, we want to start by taking our derivative, right? So f prime. So this is just a nice polynomial, so we're going to be doing the polynomial rule, right? So we got 3 times 3 to the x, sorry, times x to the 3 minus 1, minus 3 times 2x to the 2 minus 1, plus 1 x to the 1 minus 1, and the derivative of negative 1 is 0. So I'm going to clean this up a little. So this is 9x squared minus 6x plus 1. Okay. So then once I have my derivative, I want to find where is that derivative 0. All right, so that'll be the critical points. So this is a quadratic. In particular, it's a polynomial, so the easiest way to find where it's 0 is to factor it, but it's a quadratic, so I can use that AC method or whatever method. Regardless, if I factor this out, this is going to end up with, let's see, 3x minus 1 times 3x minus 1. Okay. And to be sure, you can sort of FOIL it out, right? So I get 3 times negative 1 and 3 times negative 1. That'd be the negative 6. Negative 1 and negative 1 gives me positive 1, and 3x times 3x gets me 9x squared. So it works. Okay, so this tells me that I have a double 0. So in particular, I have a 0 at x equals 1/3. So then I want to take this thing and use a sign chart, right? So this gives me the critical point of 1/3. So I'm going to use the sign chart to see whether or not that critical point is actually a max or min. So the only 0 I have is at 1/3. So then I'm going to take the sort of sign, right? I'm going to look for a thing on the left versus a thing on the right. Since I can pick anything on the left, I'll pick something really large, so I don't really have to compute. So I could pick negative 1 billion, in which case subtracting or adding 1 won't do anything. So I'm going to get 3 times 1 billion, negative 1 billion is negative. Same here, so I'm going to get 2 negatives, so it's going to be positive on this side. And if I pick some giant positive number, like positive 1 billion, then I'm going to get 3 billion. The minus 1 does nothing, so that's positive. 3 billion again, negative 1 does nothing, so that's positive again. So I'm going to get positive on this side. So in particular, 1/3, although a critical point, is not actually a max or a min, right? Because it doesn't change sign. So this tells me there's no local max or mins on the sort of natural domain. I do have to sort of be careful and double check that I wasn't given a restricted domain, right? Because then I might have to check endpoints. But here, I don't have any restricted domain. So this tells me there are no local max or mins. And the lack of any kind of restricted domain means that since I have no locals to check, I also have no absolute or global max min. And that's it. So I checked my derivative, found where it was 0. Those gave me my critical points, and then I did the sign chart, but there were no places where it changed sign, right? So this thing is sort of strictly increasing. It never sort of dips down to make a max. It never sort of goes from going down to going up to make a min. So this thing has no max or mins. It has no endpoints to check. There's no extrema. That's that. Hello. So in this example, we are finding max and mins, local and absolute. So we're given a nice polynomial. So first step, right, is to take the derivative so that we can check where the derivative is 0, which are the critical points, but we want to find really where the derivative changes sign, right? So we're going to take the derivative, factor what we get, make a sign chart so that we can find these parts. Okay, so start with finding f prime. So the derivative, I'm going to have 1/3 times 3x to the 3 minus 1 plus 6 times 2x to the 2 minus 1 plus 27 times 1x to the 1 minus 1, and derivative of negative 17 is just 0. So then I clean this up. So the 3 and the 1/3 cancel, so I get x squared plus 12x plus 27. So again, I need to find the zeros, so that means I want to factor this thing. However we want to do that, this is a polynomial, so we have a lot of tools for factoring, but it's a quadratic, so it's even easier. So here I can use standard coefficient method, for example. Two things that multiply to 27 and add to 12, so that's going to get me x minus 9 and plus 9 and x plus 3. Okay, and that gets me as zeros, x equals -3 and -9. So now that I have my zeros, I want to write, these are the potential points, these are the critical points, but I'm going to figure out by using a sign chart. So I'm going to mark where these are, so I'm going to get a -9 over here and a -3 over here. Again, I only need to write down the actual zeros. I don't need like a 0 mark or anything like that. And then I'm going to plug in points-ish to test these things. So in particular, if I need something far to the left of -9, I can pick something gigantic so I don't really have to compute anything, right? So if I take -1 billion, the plus or minus 9 or 3 does nothing. So the -1 billion is going to make that negative, it's going to make that negative. Product of two negatives is positive. Something to the right of -3, so I could take +1 billion. Again, adding or subtracting won't do anything, so I'm going to get positive and positive, so that's going to be positive. And the only one I have to sort of be careful about is the one in the middle now. So I could take the nice middle, -6. So -6 plus 9 is positive. I don't actually need the number, I just want to know if it's positive or negative. So that's going to be positive, plus 3, so -6 plus 3. The -6 is bigger, so I'm going to get negative. So positive and negative, I'm going to get negative. All right, so this tells me that at -3 and at -9, both of these numbers have sign changes. So they are both max or mins. And a nice easy way to check is to just sort of draw representative slants, right? So if this is a positive curve, it's going up, and this is a negative curve, it's going down. Same over here, it's going sort of down on the left and up on the right. So this thing is going up, so this is going to be a max. This thing is going down, so this is going to be a min. Okay? So this means that I have a local min at x equals -3, and I have a local max at x equals -9. So then, so remember, I want to find all of the local and absolute max and mins, not just where they are, but what they are, right? So I have to actually plug these values in. So in particular, I'm going to have, in fact, I'll change my color again. I'm going to have a minimum at -3, comma, f of -3. And then I'm going to have a max at -9, comma, f of -9. Okay. So that means I need to calculate these, right? So in particular, I need to calculate f of negative 3. And notice I'm not using the derivative. I want to use the actual function, right? The actual f in the problem. So this is going to be 1/3 times negative 3 cubed plus 6 times negative 3 squared plus 27 times negative 3 minus 17. Okay, so this is going to be 1/3 times, so one of the 3's will cancel to -1, and then I'll have another negative 3 squared, so that's going to be -9. Here I'm going to get 9 times 6, so that's 54. Here I'm going to get negative, 81 and negative 17. So I'm going to get, let's see, negative, negative, negative. So negative 90, negative 107 plus 54. Ugh, that's, 63? Negative 63. If I did that right, which I didn't. Sorry, should be. Try that again. So negative 90, negative 107, so that should be negative 53. There we go. All right, so that tells me my minimum then. -3, comma, negative 53. Okay. And I'm going to do the same thing for the max. So I need to do 1/3 times negative 9 cubed, which is some gigantic number, plus 6 times negative 9 squared, plus 27 times negative 9, minus 17. Oh boy, so this is 1/3 times negative, so that's 81 times 9 is 729, plus that's going to be 81 times 6, so that's 486. And 27 times negative 9, so that's going to be negative, so that's going to be 9 squared times 3, so that's going to be 243. So minus 243 minus 17. Okay, so this is going to be what? Also 243, so this is negative 243. So negative 243 is 486. So this, and that cancels. So I'm going to actually end up with just negative 17, which is madness. So I'm going to end up with a max at -9, -17, assuming I did that number crunching correctly. All right. Now, keep in mind, these are from the sign chart, right? So what I've done here is I've found the local min and max. So in particular, I should make note of this, these are local or relative min and local or relative max, okay? Now I only have one min and one max, so I would be tempted, or I could be tempted to say, well, if I only have one minimum, that's the absolute minimum. If I only have one maximum, that's the absolute maximum. But that would be incorrect, right? Because this is one of those things we mentioned that, like, it's really easy to get so wrapped up in doing the computation that you sort of forget to even check if there is an absolute min or max. And in fact, our function is a cubic, right? So our function actually looks like something like this-ish, right? Where we have that max over here, the min over here, but since it's a cubic, it's going up in one direction and down in the other. And so this thing is actually going in opposite directions, which means it's going to positive and negative infinity. There's no absolute there's no absolute minimum and there's no absolute maximum because we have no restricted domain, okay? So we found the local min and local max, but we can sort of, and we could have said this before we did anything, we can say there is no absolute or global min or max. Okay? So this is a nice thing for polynomials. In fact, something you probably learned in pre-calc, depending on where you took it, that sort of with polynomials in particular, you can actually tell whether it has absolute mins or maxes just by looking at the degree, right? So odd degree polynomials never have absolute mins or maxes unless there's some restricted domain part, okay? So no absolute or global mins or maxes, but we do have a local of each. And that's that. Hello. So in this video, we are going to find all the local and absolute maximum minimums of our function. So as sort of usual, we're going to start by taking the derivative and finding when that derivative is 0 so we can find our critical points, but sort of more importantly, so we can build the sign chart to see where they sort of change direction, right? So start by calculating f prime. So in fact, even before I do f prime, I'm going to rewrite f in a way that makes it sort of easier to take a derivative, right? So I'm going to say, okay, f of x, which is this square root thing, I'm going to write it as 2x squared plus 4x plus 3 all to the 1/2, right? That way I can use my power rule, polynomial rule, whatever you want to call it. So then when I calculate f prime, that's going to be sort of using that rule, so bringing down the 1/2 times that inside, 2x squared plus 4x plus 3 to the 1/2 minus 1 times, and then the chain rule, right, tells me I want to do the derivative of 2x squared plus 4x plus 3. And to be clear, this is the chain rule. So then I can write this as 1/2 2x squared plus 4x plus 3 to the negative 1/2 times, and then this is the same deal, so 2 times 2, so that's 4x to the 1 plus 4, and then the derivative of 3 is just 0. And now I'm going to write that in a different way to make it a little clearer what's happening, because here this is a negative power, so this is really this thing on top, 4, I write that as 4 times x plus 1, right, factoring out the 4. But all of this stuff and that 2 all go to the bottom, so this is really 2 times the square root of 2x squared plus 4x plus 3. And now so now I've taken my derivative, right? And my goal now is to find where this thing is 0, but I also need to know where this thing does or doesn't exist, because that's going to be part of the sign chart, right? So I'm going to sort of clean this up a little more. In particular, I can sort of cancel 2, so I'm going to have 2 times x plus 1 over square root of. So now this thing is a quadratic inside, and I need to know when that's going to be 0, because that's going to determine sort of whether or not this thing is going to be sort of trying to divide by 0, right, which would be a bit of a problem. So really, I need to be able to factor this thing. Now, looking at this, I could try an AC method, but that means I need 2 things that multiply to 6 and add to 4, and that's not going to work. So instead, I'm going to have to use my quadratic equation. So here, I'm going to have minus b, so I'm going to do this over here. I'll do it in a different color. So I'm going to have minus b, so that's negative 4 plus or minus square root of, let's see, so that's b squared, 16 minus 4 times a times c, which is 6, all over 2a, so that's all over 4. So that's minus 4 plus or minus square root of. Now I have 16 minus 24, so that's going to be negative 8. But this already tells me then that this is not a real number. So since that's not a real number, this tells me that this thing is never going to be 0. And in fact, this thing is going to be positive for all x. Okay? So since that thing is never 0, and we can see obviously for say x is 0, I get 3, which is positive. So it can never hit 0, so it's either always positive or always negative. When x is 0, this thing's positive, so it's always positive. So that means that really I don't have to factor this anymore. I can leave it as 2x squared plus 4x plus 3, because I know that that thing is never 0. So I don't have to worry about when it doesn't exist. So that means I can now do my sign chart. And the only thing I have is when x is negative 1. But when x is negative 1, what happens? Well, I can pick some very, very large negative and some very, very large positive, plug it in and get my signs, right? But as I was just saying, what that tells me is that the bottom is always positive, right? So since the bottom is always positive, it really only matters here. And if I plug in, say, a giant negative, then the plus 1 does nothing, the times 2 doesn't change the sign, this thing stays negative. If I plug in a giant positive, adding 1 does nothing, multiplying by 2 doesn't change the sign, I stay positive. So I have a negative, then a positive, so this thing has a minimum at negative 1, okay? So minimum at negative 1 comma f of negative 1, which means that I need to plug in negative 1. So I'm going to look at f of negative 1, which equals 2 times negative 1 plus 4 times negative 1 plus 3, sorry, negative 1 squared, all square rooted. So this is 2 minus 4 plus 3 square rooted, which is 2 and 3 is 5, minus 4 is 1 square rooted, which is just 1. So this is a minimum at the negative 1 comma, and then I got 1 as my positive, as my function evaluation. Okay. So this gives me a local min. So then the question is, what happens if I try to do an absolute, right? So what I found is there's one minimum, one local minimum. There's no local maximums, and then I have a question of absolute mins or maxes. So on the one hand, I have a potential restricted domain because I have a square root, right? But we've already sort of addressed that because that's exactly the square root that we just checked, and there's no place, right? The restriction would be the inside has to always be non-negative, meaning it can't be 0 or negative, but we've already discovered, right, that it is always positive. So there's actually, as it turns out, no natural restriction because the inside polynomial is always positive, which means the square root is defined for all of the x's. I don't have to worry about that part. But I do need to think about the end-term behavior, right? So I need to know, okay, what happens as x gets infinitely large? And this is one of those things where like we can compute it, but really if we think about it, as x gets infinitely large, well, it's going to, the inside is going to behave like just the lead term, right? That's the whole thing with polynomials. This thing's going to act like 2x squared. So whether x is positive or negative, it's going to get big and positive, but then it's going to get square rooted. So it's really going to behave like 2 times, well, square root of 2 times x, meaning it's going to basically just act like x, but positive in either way, because the square is going to sort of make it positive before the square root lands. This is really going to behave in an end-term situation like absolute value of x, meaning that this thing is going up, up, and away in both directions. So I have a local min, I have no local max, I have no absolute, so I have no local max, I have no absolute max, and because the thing goes up, up, and away in both directions, I know I have an absolute max, an absolute min, and the only place that could possibly occur, since there's no domain restriction, is here. So this is local and absolute min at negative 1, 1. Okay? So that is that. Hello. So in this example, we are finding all the local and absolute mins and maxes, but now we have a sort of more interesting function, rational function. But the process is still the same. We're going to take the derivative, find where the derivative is 0, use that to make a sign chart to see where we change directions. Okay? So let's roll. So here, right, we have our f. So just as reference, because I'm going to be using this sum, it's easier for me to see in my own writing. So we have x squared plus 3x plus, no, minus 4 over x squared plus 1. All right. So we're going to start by taking a derivative. So I think that one didn't work well. Oops, I wrote that was a derivative when I meant that was just f. Sorry, I was on a bit of an autopilot there. So in particular then f prime of x. So taking the derivative, right, this is like a quotient rule, or you can do the product and chain rules, whichever way you like. So here I'm going to do x squared plus 1 times the derivative of the top, which is 2x plus 3 minus the top, x squared plus 3x minus 4 times the derivative of the bottom, which is 2x, all over the bottom, x squared plus 1 squared. All right. Now, I need to be able to find where this thing is 0. And in fairness, I also need to know where this thing doesn't exist, where any domain restrictions are, because I need that for the sign chart too, even though I know those won't be max or mins. But it turns out the bottom, right, is x squared plus 1. So something squared is always positive for real numbers. Plus 1 means it's not 0 ever. So this bottom is always going to be at least 1 and a positive number, meaning I don't have any domain restrictions from that. The top is a polynomial, albeit in a strange form at the moment, so I'm not going to have any domain restrictions there. But to be able to actually factor this thing, I need to expand everything out and combine like terms before I do anything else. So that's what I'm doing next. So I'm going to expand all of this out. So foiling, I'm going to get 2x cubed plus 2x plus 3x squared plus, so that was 2x cubed plus 2x plus 3x squared plus 3 minus, so then I'm going to have 2x times that, so I'm going to get 2x cubed plus 6x squared minus 8x all over, and I can leave the bottom factored because I don't have to worry about the bottom here. As I said, it's never 0, which is what I really care about. So then I can combine like terms, but I want to make sure I distribute this negative while I'm going. So the 2x minus, so 2x cubed minus 2x cubed, those are going to cancel. So this with the negative cancels with that. Then I have 3x squared minus 6x squared. So I'm going to get minus 3x squared left over. Then I have 2x minus minus 8x. So that's going to give me, let's see, 2x minus minus, so that's plus. So I'm going to get plus 10x. And then I have just the 3. There's no constant over there, so I'm going to have plus 3 over x squared plus 1 squared. All right. So then I need to do the, I need to factor this thing in some way. So again, it's a polynomial, but it's a quadratic, so I could try something like the AC method, for example. So then I would need two things that multiply to -9 but add to 10, which is not gonna happen. So another way I could do this is b squared minus 4ac. So that would be 100 minus 4 times 9, which is 36, so 136. So it has real roots, but they're annoying. So this tells me that I'm going to need to do quadratic formula because they're not going to be rational. All right, so let's do that then. So I'm going to do that over off the side here as sort of scratch work. So I want minus b, so that's going to be minus 10, plus or minus square root of b squared, so that's 100, minus 4 times a times c, so -3 times 3 is -9, all over 2a, so that's going to be -6. So that's -10 plus or minus square root of 136 over -6. So if I split the -6, I'm going to get 10 over 6, which is 5/3, plus or minus. And then let's see, 136, so 4 goes into that. 4 goes into that 34 times. So I'm going to get 2 root 34 over -6, which is 5/3. So the negative can come out and it just flips the plus or minus to become minus plus, but really it won't matter because, right, I'm adding and subtracting this value. So whether I'm adding and subtracting the negative or adding and subtracting the positive, I'm going to get the same two values just in a different order. Regardless, I'm going to get square root of 34 over 3. Now, I know square root of 34 is going to be bigger than square root of 25 and less than 49. So that's going to be between, bigger than 25, less than 36. Pretty close to 36 though. So this is close to 6, meaning this is close to 2. So if I look at this, I'm going to get something that is sort of a little bit less than, let's see, 11 thirds, and something that's like just on the negative side of 0. Really what I need to worry about here, because all I'm really going to care about is the sign chart, right? So using that, I'm going to get, so in particular, I'm getting as my zeros 5/3 plus square root of 34 over 3 and 5/3 minus the square root of 34 over 3. So that means if I do that over here, I'm going to get something like you know what, I'm not actually going to worry about it. So I could write this with the factor form, but I don't need to. These are the things I need, the zeros. So now that I have the zeros, I need a sign chart, right? But I need to know where to put these things on my sign chart. So this is why it's sort of helpful to ballpark this, not because I'm trying to get an exact answer, right? And I don't need a calculator. What I need is to have a number. I need to get sort of a value close enough that I know how to pick values for my sign chart. This is why I was saying the square root of 34 is very close to 36, right? The square root of 36, and that would be 6. So this is close to 6 over 3, meaning this is close to 2. So this is about 5/3 plus 2, or 11/3. And this is about -1/3. So my two zeros, I'm going to have one here and one here, right? Where the actual zeros are 5/3 plus square root of 34 over 3, and 5/3 minus the square root of 34 over 3. But I picked these, so I did this to think to myself, okay, if this is around 11/3, then what I'm really looking at is I want something that is way bigger than 11/3, something that is between 11/3 and -1/3, but not near those two values because these are approximate. So I would pick something like 5/3, right? Because I know that I'm subtracting a value from 5/3 and adding a value to 5/3, so 5/3 is in the middle somewhere. And then I need something to the left, so I'm going to pick some very large negative number so that I am way to the left of whatever that approximately is. Okay, so that's how I'm going to do my sign chart. I don't need to know these exact values. I can estimate them just so that in my head I can pick a value that sort of I know is between them. So I want something that's sort of between these values, but not near them because they are estimates, right? And I don't want to be like, I'm going to pick, something really close to -1/3, and then it turns out that my estimate puts me on the wrong side of the line or whatever. I don't want to have that happen. So I'm going to pick something that's truly sort of in the middle as best I can. And in fact, I could pick 5/3, but I could also pick like 6/3 would be a good one, right? Because that's far away from either of these. 6/3 is 2. That would be nice and easy to calculate for the top here. So I'm going to pick some giant negative number, like -1 billion, right? So if I pick -1 billion and look here, well, the bottom is a thing squared. So the bottom's always going to be positive. I'm never going to have to worry about the bottom. In the top, if I take -1 billion squared, I'm going to get a positive thing times -3. So I'm going to get some truly massive negative number here, way bigger than either of these terms, right? Because the leading term dominates eventually. So if I picked -1 billion, then this term is all that's going to end up mattering, and that tells me I'm going to get negative. Likewise, if I pick some positive massive number, then again, the leading term is going to dominate the rest, right? This is a property of polynomials. So that tells me that eventually this thing is all that matters, right? So the bottom is positive. These aren't going to contribute enough to overcome whatever happens here. And for +1 billion or whatever, I'm going to get the negative 3 times 1 billion squared, which is going to end up being negative. So this side is also negative. Now the tricky one comes in the middle. I could use 5/3, which is definitely between the two because I'm doing 5/3 plus or minus. But I know this is big enough that 6/3 would also be between. And so I can plug in 2 and actually see what happens, right? Now, because it's not factored, I actually might want to calculate the 2 just to be certain. So if I plugged in 2, I get 2 squared is 4. 4 times -3 is -12, plus 20 plus 3. So -12 plus 20 is already positive, plus 3 is icing on the cake. This is positive. Excuse me. So this tells me that I have, right, a negative slope here, a positive slope, and then a negative slope. So I have a min here, and I have a max here. But I need to actually calculate what these things are, right? Because again, it wants to actually know what the local and absolute maximums are. Okay, so that tells me I'm going to have a min at, oh boy, 5/3 minus square root of 34/3, comma, f of 5/3 minus square root of 34/3. So that means I have to calculate that. So f of 5/3 minus square root of 34/3 equals what? Well, that's going to be unpleasant. So I'm going to put these in one fraction because it's going to make my life a little easier. So this is going to be 5 minus square root of 34 over 3 squared plus 3 times 5 minus square root of 34 over 3. So I'm plugging into f here, right? Minus 4 over 5 minus square root of 34 over 3 squared plus 1. Okay. So the good news is that that 3 and that 3 cancel, so I'm not going to worry about that. This I'm going to have to unfortunately FOIL out. So that's going to get me, let's see, 25 minus 10 root 34 plus 34 all over 9 plus, and then I'm going to get 5 minus 4, so that's going to be 1 minus square root of 34 over, and now this is the same as that, plus 1. So I'm going to get this thing plus 1. 25 minus 10 root 34 plus 34 over 9 plus 1. Oh boy. All right. So then, so I'm going to do a little tricky thing here where I'm going to multiply everything by 9 because that'll clear out those 9s, but that means I also have to multiply these things by 9. So if I do that, I'm going to get 25 plus 34, so I'm going to get 59 minus 10 root 34. And then, so I multiplied this by 9 to get rid of the 9. So to be clear, I am multiplying by 9 over 9 in order to cancel that 9 and that 9, but then I still have 9 times this and this times 9 left over. So that is this, but then I also have plus 9 minus 9 root 34 over, and then I have the same deal, so 59 minus 10 root 34 plus 9. This is a hideous problem. All right, so putting together all my like terms finally, so I'm going to get 68 minus 19 root 34 over 68 minus 10 root 34. All right. So this is my value. So I have a minimum at that beast, which is pretty bad. Now I'd also have to do the max. So I'm going to write that over here, max at, and this is going to be 5/3 plus square root of 34 over 3, f of 5/3 plus square root of 34 over 3. So in particular, this is, in fact, I'll do this in a different color. So I'm going to write sort of the actual result. So I have 5/3 minus square root of 34 over 3, comma, 68 minus 19 root 34 over 68 minus 10 root 34. Okay. So my claim is going to be that I can do this sort of quickly, and I encourage you to go through the computation the same way we did here. But I'm going to claim that this is, let's see if I can do this in my head like a wizard. So this is going to be 5/3 plus square root of 34 over 3, comma. So let's see, I'm going to end up with, so I'm going to end up with 68 plus 19 root 34, I think, over again, I think this is going to be 68 plus 10 root 34. And that's going to be the max, okay? Okay. All right, so this is to show, right, that you might get gross numbers, and I am willing to be right there with you because this is unpleasant, right? But again, I hope even if sort of the numbers got a little rough, and feel free to like pause and work through it and follow along with me. And but even if the numbers got kind of rough, I hope that you see the process is still the same, right? We went through it, we had to find where the thing was 0, use that to make a sign chart, mins and maxes. Now, these things that I found are local mins and maxes, right? So this is a local, and this is a local. And we want to know, are these things absolute mins and maxes, right? So to find out if they're absolute mins and maxes, mins or maxes, we need to know what's happening, right, with the function, sorry, the original function. So in particular, there's nowhere, right, because we have x squared plus 1 on the bottom, so there's nowhere where this thing is undefined. But we need to know about the end-term behavior, meaning we need to look at the limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. But if we sort of go through that process, right, and we can see the end-term behavior, this is polynomial over a polynomial, so however you want to do that, dividing by a nice power of x, for example, or doing L'Hopital's rule if you have that in your class, or doing stuff from pre-calculus, regardless, you'll find that the answer to both of these is 1. So since these things are finite, that tells us that if either of these values are sort of bigger or smaller than that, respectively, right? If the max is bigger than 1, and if the min is smaller than 1, then those are actually going to be absolute mins and maxes. And in fact, we can sort of see immediately that the top here is bigger than the bottom because it's bigger by 9 root 34. And over here, this thing is subtracting a larger value on the top. So it's going to be smaller than 1 here because I'm losing more on the top than I am on the bottom. So what that tells me then is that these are both of them are both local and absolute. Local and absolute mins and maxes. Okay. And that's all of it. So we found the locals, we used end-term behavior and checked to see where it might not be defined, which was thankfully, it was defined everywhere. And then using some logic, right, the fact that the end term was 1 and the fact that our max was bigger than 1 and our min was less than 1 told us that those are both local and absolute mins and maxes. Okay, so that is that.